Hello student, welcome to the Web Optics course. So today we will going to have our lecture number 15 and we will going to continue the concept of coherence. For last couple of weeks last couple of classes we are doing this concept, try to understand this concept. So let us continue with that. So we have today lecture number 15 and we are going to study the concept of coherence again. So let me remind what we have done so far, that if we have one source point S and the waves are emitting from this source point through another two source point S1 and S2, say this is S1 and this is S2, and it is reaching to some point P, then the two waves that is coming from the source S1 and S2 will going to superpose at this point P. And after doing all the calculation, we find that if we try to write down the intensity at the point P, I can write it the intensity in this way. The superposition of these two waves will produce the intensity at point P in this way. And then we have an interesting term called real part of gamma tau, where this real part of gamma tau determines the degree of coherence, that the light that is coming here, how they are going to interfere themselves at the point is basically determined by this. So what was real part of gamma tau? We calculated that in last class. I can write it as some amplitude, and since it is a real part, I write cos of omega tau. That was the value. And what was in the amplitude? The amplitude of this gamma contain term 1 minus tau by tau naught, but tau naught was the coherence time, and this quantity is basically determine the degree of coherence. We remember that if this is the general form, then we can find out something called visibility. We defined that visibility was I max by definition minus I mean divided by I max plus I mean. So the coherence, the degree of coherence is something to related with this visibility, and we checked that 4 conditions in the last class, that what happened if it is a completely coherence, if it is completely incoherence, and thirdly in between these two, either it is in between completely and in between, this means the gamma value is neither 0 and nor 1, in between that value. So this visibility, by the way, if I write in this form, then from this expression I can write it as, that this maximum value gives me maximum minus minimum. If I calculate, then there is a cost term. So based on this, I can write something like I max minus I mean, that means IP max minus IP mean, and the maximum and minimum value is determined by this cos omega t term, cos omega tau term. This, if the cos omega tau is plus 1, then that should be the maximum, and minus 1, then that should be the minimum. And if I put this together, then what I get is this. It is 4 in the numerator we have 4 root over of IP 2P, and then we have this mod of gamma term divided by this plus this. The interference term will cancel out and we are going to get 2 of this. That is a general form of V in terms of gamma. Now what happened if IP 1P for the same source, say this is I0. If that is the case, I can write V is equal to this 1 2 will cancel out, so it should be 2 of I0 divided by this 2 is not there, so it is 2 of I0 then gamma mod. So the visibility is essentially determined by the gamma naught when two sources are same. And now 3 conditions I can put together. So one, when gamma is equal to mod of gamma is equal to 0, that means it is completely incoherent. Then what we have, the visibility is 0, incoherent. Second is when mod of gamma is equal to 1, that is the degree of coherency I am writing here in terms of gamma, that is it is coherent, completely coherent. Then V turns up to be 1, the visibility is now have a maximum value. And finally, when gamma is in between, mod of gamma is neither 0 nor 1, but it is in between, then it is called partially coherent. In that case, the V will be equal to the value of the gamma that it takes. So the degree of coherence tells us whether two waves, when they interfere at some point P, it will be exactly coherent or exactly incoherent, or they are partially coherent depending on the value of this gamma. The calculation we had already done in our previous class. Now what we go from this, we will try to understand another type of coherence, and that is called the spatial coherence. So today we will going to discuss about the concept of spatial coherence. So what is spatial coherence? So it is basically the correlation in phase between two spatially distinct points of the radiation field. So, if for example I have a absolute point source, say S, it is absolute point source, and from this source the radiation is emitted and it is falling on, say, on the screen having 2 point A and B. So, the point A and B here, whatever we have drawn, are spatially coherent if S is true point source. A and B are spatially coherent if S is a true point source. What is the meaning of that? That means there is no spatial distribution here over this source, and if there is no spatial distribution over this source, then the definition, the correlation of the phase between two spatially distinct points, here there is no two distinct point, it is only one point. So, since there is only one point, automatically these 2 point A and B has proper phase relationship. So, that is why A, B are called spatially coherent. However, the situation is slightly different if we have a distribution. Suppose the source has a distribution like this. Distribution means this is a extended source. Suppose this is a extended source. What is the meaning of extended source? I can consider many point source over that. Here we have only one point source, but it is extended source means it will be the collection of many point source, and they are mutually incoherent sources. That means these sources are emitting light, but this light doesn't have any phase relationship among them. So, extended source, and it can be this extended source in general can be treated as a collection of mutually incoherent point sources. So, that means the wave that is emitting from this point and the wave that is emitting from the other point, they do not have any phase relationship between them. So, the lateral this lateral dimension of the source over which the radiation remain correlated in a space is essentially the measurement of the spatial coherence. That means among this extended source, there are, suppose we have another point here, and these 2 points maintained that this is the highest distance, lateral distance, among which the 2 points on the source, extended source, they maintain their phase relationship. So, these 2 are considered to be the spatial coherence point. So how you measured that, how you quantified that, that is interesting, and that we are going to do next. So suppose we have an extended source, and this is the extended source dotted line, and I take 2 points. One is say S, this is the point S, and another point is S prime. Over the lateral distribution, this S and S point are located over this extended source. Now from S the radiations are coming, and we have say 2 points A and B, and it is going like this. I put a dashed line. So here we have A, here we have B, like some sort of double slit kind of experiment we are doing here, and then over a point P it is reaching, or over a point O it is reaching. This is O. Over the screen, say I define this like sigma. So what is happening here? S is a point, and light is emitting from here, hits the point A and B. Suppose there is a pinholes, and then the light goes to point O, superimpose, and they are superimposing there. So this is, we assume this is an extended source, and this length say D, and this is the axis, and this length A to B, we consider this to be 2D. Okay, the similar thing can happen, since this is the extended source, not only from the S but from S prime also the light can emit, and if it does, then it goes like this. Let us draw this by this solid line. So here this is the 2 ray that is coming from the point S prime, and do the same thing from here, it goes to over O and they superimpose. So now we need to find out the condition for which S and S prime does not have the minimum length of S and S prime, where they don't have any phase relationship. So so suppose each source point S and S1 is producing the its own interference pattern at point O. So let me write down here, each source, in this case it is S and S prime, produces its own interference pattern on the screen. Gamma, this sigma. So now SA, we know that SA is equal to SB, and AO is equal to BO. So that means S is producing a maxima around this point O. So the point source S is producing a maxima around O. Now if S is producing some maxima, then we need to check what happened for the other wave, that is what happened that for the other source S1. Will the S1 produce a maxima or minima? However, depends on the path difference between S1B and S1A. So the intensity at the O depends on the intensity at O due to S prime will depend on the path difference. And here the path difference means, if I write delta, that path difference is S prime B minus S prime A. Now we can put some geometry here. So I can have S prime B square using the Pythagoras theorem. You can readily find S prime B whole square is D square plus D square plus 2 this plus this L, say let me write this as L, so L this is so this is okay. So I need to define this as well. So this is the length between separation between these two. I need to put, otherwise I will not be able to calculate that. So now if I put, then it should be D square plus L plus D whole square, because D is from this to this point and I am calculating this. So D square plus L plus the length that is here from this. So this is D. So this will be S prime B square. So I can write this as D square 1 plus L plus D divided by D square of these things. Similarly, S prime A square of that is D square plus L minus D square of it, which I can write D square then 1 minus 1 plus L minus D whole square divided by D square. Now this quantity D minus L or L minus D, whatever, divided by D, this quantity is very less than 1. because this source, they are very close to each other, and these points also we consider to be very close compared to the length between this point and this screen. So normally that is the condition we always have in double slit experiments. So this condition always hold. If that is the case, then we can simplify this quantity S prime b, and S prime b will be d into, let us first write in this way, then we put our approximation, plus d plus L divided by d square of that whole to the power half. This is essentially d plus half d plus L whole divided by d. Similarly, I can write S1 S prime A is nearly equal to d plus half d minus L whole divided by d. So the path difference delta, which is equal to S prime B minus S prime A, is essentially this minus this. If I do so, there is a square I missed here. This will be a square. It is essentially 1 divided by 2d and then 4 of d of L, or that is 2d L divided by d. Now we will going to get a minima, so we can get a minima at the point O when the path difference delta will be equal to lambda by 2. Okay, the lowest value I can take also multiple of lambda by 2, that is the condition for which we can get the minima, but let us take the lowest one, it is lambda by 2. So in that way, S will produce a maxima there and S prime is produce a minima there, so no fringes will be there because of that condition. That is the condition where, so no interference pattern will be there because of this. Now if that is the case, that it is S prime is producing a minima there, then what we are getting is 2d of L divided by d, that is equal to lambda by 2. So that is the condition that no interference, no pattern will produce at O. So from here we can find out the separation of the source, which is half of lambda d whole divided by 2d. So we can find a value of L, that is the separation between these two source point, for which we are going to get no fringes at the point. So L is here half S and S prime, and L is that value, half of lambda d divided by 2d. So that means for an extended source, if I want to find out an interference for good interference pattern, we required that extended source, the separation between 2 points for extended source should not be very close to the value lambda d divided by 2l, rather much smaller than that, because the last case we find that this is a half term. So for each source we have another source in the opposite direction such that this condition is satisfied. So in general it should be L should be very less than lambda d by 2d to have a good interference. So if I draw that, S and S prime, they should, so here we have the slits A and B, and geometry wise this is my D and this separation is L. So if I calculate what is the angular separation one can have from these 2 points, so this angle, if say is theta, and this is our 2D, that is the geometry we have. So 2D we already find that it has to be very less than lambda d divided by L. Same equation I am writing here. So then 2D has to be very less than, if I write in terms of angular separation, it should be lambda divided by this theta. L, because here we can see that L is equal to d into theta for small theta, and theta is equal to L divided by d. So that value I put here, L divided by theta. So that is the angular separation. So lambda divided by theta, that is the length, I write LW, we call is as lateral distance over which the beam may be assumed to be spatially coherent. So that is the length for which we can consider that the beam can be considered to be a spatially coherent beam. So for for a circular source, however, so for a circular source, that is, so LC is around 1.22 lambda divided by theta. This we will going to discuss later when we discuss about the array function and all these things. So that is the separation one can have, one can consider if we want to find out what happened for spatially coherent case. So if the source is single point source, then we will going to get spatially coherent. If it is not, then it is not a spatially a coherent thing. So quickly, if I draw that what happened when a spatially coherent beam and a spatially incoherent beam is propagating. So this is the way one can expect the propagation of spatially, and so we have a point source here and the light will propagate like this. In all space point we have a well maintained phase relationship. So this is the way the light will propagate when we have a spatially coherent light beam. However, for spatially incoherent light beam, this is a Z and this is say over X. So this is X and this is Z. The light will propagate and then suddenly there will be a phase distortion and it will be like this. So there will be no phase relationship if it is incoherent kind of wavefront moving from incoherent kind of source. So this is the way the coherent and incoherent beam will going to propagate in space when we have in terms of spatially coherent and incoherent. So today we're going to understand. So we don't have much time today to discuss more about this. So we're going to discuss in the last couple of classes, which is important, that how the light when interfere to each other, then how the coherency, the property called coherence is important to find out whether they will produce a very nicely looking interference pattern or not. So that is a major criteria, that if two light interfere into each other, they will produce a very nice looking fringe, and this will happen when they have the coherence property in them. So the degree of coherence we calculate, for which we can find that when they are absolutely coherent, they will produce a very nice fringe. In terms of visibility, the term is 1. If they are not coherent at all, they will not going to produce a very nice looking fringe. In fact we will not going to get any kind of fringe pattern out of that, and that's why the visibility is almost 0 there. But we can also get in between the condition where the visibility, we have a partial visibility and the degree of coherence determine what is the value. Also we learned that what is the meaning of spatial coherence. If we have a point source and it is emitting light, so that light when it is propagating the wavefront, they have a well maintained phase relationship among them. But if we have a source that is emitting light, but it is an extended source, the 2 point that is emitting the light, if they are not spatially coherent, then the wavefront that is moving is not precisely having among the phase front in this propagation, they don't have a precise phase relationship among them, and we call this incoherent coherence. So incoherent radiation. So in two slit experiment, this is very important, that the light should be spatially coherent to get a fringe. In the next class we will discuss more about in detail that when two light will going to interfere, then what should be the pattern, and how for two slit case the patterns are formed, etc. With that note, I'd like to conclude in today's class. Thank you very much for your attention, and see you in the next class.